Okay, so what's dynamic linking? The idea behind dynamic linking is pretty simple. It's a way to extend what a program does, its functionality, on runtime, instead of during build time or compile time, which is really wrong to say because it's actually the linker that does the adding together of the pieces. You can use this ability to break down one big program into several modules, and this is very useful for several reasons. First, it allows code reuse. It allows you to build a program which logically is built of several parts, which is good because one of the big problems when you run big programs is to control the complexity of it. Technically, it's not really unlike what happened in static linking. Static linking is what happened when you just compile a program normally. You've got the compiler that runs over the source code into binary. Then the linker takes all the pieces together and assembles them into one coherent program. Dynamic linking is very much like this, only it happens dynamically, sometimes on the fly. And it happens with pieces of code which actually the dynamic linker doesn't know in advance exactly necessarily where they are or what their contents or length, etc. will be. By the way, if anybody has any question or something, just ask away. Okay. Typical Linux system and other systems as well have actually several cases of dynamic linking and dynamic linkers. Almost every executable usual normal system, not an embedded one necessarily, by the way, but that's a completely different subject, uses the ld.so dynamic linker to load most of the functionality of the program, including one very important one, which is very common, is of course the GNU-C library. Other examples are that the x386X server is actually built in a modular fashion, and it can load modules in runtime to satisfy certain of the dependencies it might have. Because it's a cross-platform program, they can't just use the normal LDSO linker, so they did what every normal hacker will do. They built their own. Finally, the Linux kernel actually has a dynamic linker all of its own. It's right now, at least, in the insmode utility, which loads Linux loadable kernel modules. I'm saying right now because there's a discussion with the Linux kernel main list about moving this linker actually into kernel itself, the kernel code.
It happened in 2.5.49, and it's still not working.
That's why I said it's a discussion, because until it's actually
I foresee Linux completely changing his mind.
I don't know, usually Linux doesn't like to put things in there. Now there are a lot of reasons why, a lot of good reasons to do this, but if it doesn't work...
It's one reason not to do it.
Yeah, it's one of very big reasons. Okay, let's start with a little bit of history. In the beginning of time, 1991, the format that Linux used was called AL.
What did when you say 91 at the beginning of time? What did they use in Unix in the 70s?
I think the same thing, but
the same platform.
There's a bazillion other formats. I know there's one which we'll talk about in a sec, which is called ELF, and there's others called Dwarf, and there's a bunch of them. So yeah, I'm still waiting for humans. But we're ahead of our time. So what we had then is the AL format, which not only Linux but a lot of other systems used as well. And AL was really very, very simple. Just a piece of code. There was no relocation done. That is, there was no alteration of symbols inside the binary once it's loaded. You just pick the binary, map it somewhere in the memory space of the program, and that was it. And now, of course, this creates some problems, as you can obviously imagine. If you take the binary and put it into the address space of some program and you're not doing any relocation, you're not changing where the symbols are supposed to be pointing at, obviously you can change where you map, in what address you map the libraries or other shared objects that you use. And that means that you have to, in advance, know when you make the shared library where you're going to put it in the memory map. And furthermore, you need to make sure that no other library will need to be mapped in the same location. That means you need a central authority to hand out memory region to load the shared objects into. Obviously, that's a complete mess. I mean, it means that if I write a library and you write a library, somehow have to coordinate, not getting into the same address space. Also, it means that address space is very fragmented because I'll assign you a piece and I'll get a piece, and maybe you're not using your entire piece, but still the whole that is left is quite small. If you compare it to the entire memory space, which is actually not used. But wasn't any efficient way to do it. At least not.
How many shared libraries were there?
That's the reason they use it. It's very simple, as we'll see, and there weren't that many shared libraries.
They kept it a few because of that, probably.
I don't know. It's sort of, when it got to be a problem, they switched.
That was the original format of the Unix system.
Right.
Before shared library existed in the Unix space in the 80s and the 70s.
Right. They used something that existed before even the idea of shared libraries. They just extended it to shared libraries, and then they thought, okay, this doesn't.
You don't have many cases. Wouldn't it be simple to simply duplicate everything? Anything two people use, put in twice, 3 times. Load it several times.
Maybe. Well, it's not efficient in memory wise.
Is it analogous to the COM file in the DOS systems, or it's?
I have no fucking clue. Just don't know. I think it is. I mean, the COM file is also not relocatable, right?
That's the memory map.
So it's something very similar, as far as I know.
The COM, also the exe for DOS. There is an exe format for DOS and an exe format for Windows.
So the exe format for DOS is
also, I think,
Windows is not a fully operating system.
Probably the same. I just don't know.
DOS can.
Okay, so the advantage is that layout is, of course, very simple.
Okay.
We can talk about that later. I actually do confess to know some stuff about dynamic linkage in Windows, and I don't know much, but from what I understand, it's not very pretty because there's a lot of issue. And I'm not an expert in this, so I might get this wrong. But when, for example, you have a library that allocates some memory, it's allocating the memory in a different memory space, not the one of the program. So if you, for example, use a pointer you get and try to free it, you get the equivalent of segmentation fault. It's a very messy thing. I don't know if I got it exactly right, but that's what I was told. But let's get back to AR format. So the AR format is very simple. You just put, as I said, the binary image somewhere, and there's no relocation done. In order for this to work, there's of course a table somewhere with all the symbols, and because you need to find them. You can never retire an entry in that table because you don't know which version of your shared library is gonna of the application is gonna use which version of the shared library, and it might be an old one which is used to trying to use some older version or some older symbol and use some older offset in the table, so you can never retire them. Once you allocated it an entry, you always have to keep it there. And obviously it's not very convenient because of fragmentation, because of the fact you are not very flexible with the tables, etc., etc. So there was one good thing about layout, because it was very simple, it was very fast to use it, because basically you had this table, you made a jump to the table, and you made a jump from there to the symbol you wanted. It's basically just 2 local jumps, doesn't cost a lot.
I've got another question. If I compile something in my current Linux, which is quite recent, I would probably get an A out.
No.
If I
It's called, the file is called a.out, but the executable format is ELF, unless you've done something really naughty. It's just tradition. It's just the same reason why the command that is used to print file to the console is called cat. I don't know which cat. I know it's concatenate. It's funnier in English.
The printer daemon is called line print LPR or line printer.
Okay.
TTY called teletype. Yeah, anybody here actually used the teletype? Okay. So somewhere along the way, we don't actually remember exactly when, and somebody said there must be some better way to do this. And there was another format called the ELF, the executable linkage format, which some smart people, or some would claim not so smart, but it's not me that does that claims, thought out. And the way ELF works is that you don't have one binary image of the object or the program. Instead, you have many sections, as they're called, or regions in the program with many properties. And an ELF executable format program is not complete when you first load it. There's need to be a setup phase, dynamic linking, and I'll give a short run through about what is done in that setup phase. And later we'll see a couple of interesting things we can do and we can gain because of the way it works. So as I said, an ELF program, when it loads, it's not complete. Instead, there's a small utility, which is a dynamically shared object in itself, which knows how to basically complete the program and make it, well, something you can actually run. Now, the job of the dynamic linker is not finished when the program is complete and starts to run, because there's something called lazy relocation. Basically, you only find a symbol in one of the loaded objects when you need it, when something is using it for the first time. And for this, you need to keep around the dynamic loader hanging somewhere in case you need it later. You can actually ask, there's some environment variable bind now or some sort of that will cause the dynamic linker to make all the links at load time and not do lazy relocation. I'm not really sure why it's there, but it's there. Okay, start. Because ELF is structured and comprised into several regions, the kernel can't just load a program and jump to where it's supposed to run. What really happens is the kernel will read the ELF header. There's something called the ELF header, which will tell it where to find the ELF program header, which will describe all the regions in the ELF executable format, and the kernel will load them. Now, these regions also have permissions set on them. They can be executable, they can be writable, etc., etc. And what the kernel does is actually mmaps each of these regions and will assign memory areas permission according to the entries in the header file. After we've done all that, we still don't have a program ready to run because, okay, we've got all the regions set up, but remember those regions still contain virtual symbols. They have not been relocated. We need something to go in there and change all these entries so that they will point to the actual address where the library happened to be loaded at this time. So what the kernel will do is, there's a small diversion before which I forgot about, which is important because we're going to say something interesting about it later. One of the things you can do, actually that C standard says that exist, is that there are regions in the file which are initialized to 0, static variables, etc., etc. And instead of just keeping a big block of 0 somewhere in the file and on the disk, which is a little silly, one of the tricks here that the ELF headers enable us to do is that it can define a region of memory and say, okay, fill it up with this and this part of the file, and repeat this little tidbit for until you fill up the entire region. So what you have is that you have a big region which is all initialized to 0. Basically, on the disk, it will only be 1 null. And this is useful because we know that there are variables which are initialized to 0, like the static ones. It also means that you can save up space if you have a choice between putting initial value for some variable to 0. Otherwise, it usually will be smart to put 0 in there, because that means it will not actually be allocated space on the executable file. You will get a slightly smaller executable file size. Is that very important? I don't know. Sometimes it is. On embedded systems, for example. Okay. So what happened is the kernel loaded all the regions, unmapped them, gave them permission. Now it needs to go find that magical creature, the dynamic linker. Of course, the kernel has absolutely no idea about dynamic linkers, etc. There's simply a header entry in the header that tells it, okay, go fetch this and that dynamic shared object, load it, and that is the dynamic linker. When it does that, it will relinquish control to the dynamic linker, moving, by the way, from kernel space to user space. But before it do that, it also puts on the stack some useful things. For example, it put its array of tag values, which will tell the dynamic linker where to find the program code, the region, and some other useful stuff that you will need. It's called the auxiliary vector. Okay, so the dynamic linker has several tasks, 3 of them. It needs to determine.
Why do you want? Why should the ELF file contain the location of the dynamic linker and not somewhere inside the kernel as in internal file?
I have no idea. The people that thought of ELF thought it's a good idea, and actually, you can. It means that you can make several dynamic linkers if you want them. Why not?
You
On
need
the
the one.
other hand, if you have a system in which the dynamic linker is installed in one directory and another system in which it is installed in another directory, and you try to move a binary.
Oh well, I don't think it's actually. I don't know. I think it's not really the path. It's the name. It will go look in the regular dynamic library path. So I don't think it's that. And the
Alon, does it give you a few ideas of cracking computer?
we'll get to that. Don't worry. The answer is I don't know. It sounds pretty reasonable. You can do it either that way or this way, and it makes sense to me that the L file will tell the kernel where the stuff it needs to run, instead of having it fixed in some fixed location. Then you have the problem. Okay, now I want 2 of them. What do I do? Now I need to decide which program will get which. So this way, each program just says, okay, this is the one I need. Just like it says which libraries it needs. It's just a private case of the general case that each ELF executable will say which library it needs. It will not tell where the linker where to find them, but it will tell them which one it needs. Okay, so the dynamic linker has 3 tasks. It needs to find out what dependencies actually are needed to complete the ELF program. Because remember, we only took the part, we only mapped the regions that came with the ELF file. But stuff, useful stuff, like, I don't know, printf from the GNU-C library is still not there, it's still not mapped. So we need, the dynamic linker actually needs to find out what stuff it needs to complete, and it needs to load that stuff into memory. And it needs to relocate the application and all the dependencies. It needs to go over all the places where you have a symbol written and actually somehow replace it. It's not exactly the mechanism it's done, we'll get to that, but replace it with an address, something you can actually call. And you need to initialize the applications and the dependency and do it in the correct order. And we'll talk a little bit about correct order and what that means. Now obviously, if you have fewer dependencies, you have fewer things to do, which means you've got shorter load time or startup time for a program, which is useful. And anybody who uses KDE knows that it's useful. The first and last step, this is basically everything we can do. I mean, just to lower the startup time, is just have little or less dependencies. The middle step of relocation is slightly more interesting. Load. It's more interesting because A, it's the most costly step. That's the one that takes most of the time for startup. It's not simple, and actually its complexity is asymptotically at least O of R and S, where R is the number of location and S is the number of symbol defined in all the participating objects. No, I didn't think that out. That's a paper, we'll get to that. Which, of course, means if you want to do it fast, try to lower them both. All the symbols you define, and as we said before, the number of dependencies. Okay, so how this relocation process happens. So if you remember, what we said is that the dynamic linker will start by finding all the dependencies. All the library needs to find, and go look to them in the library path. We'll load them into memory, basically mmap them at some random address. It doesn't care, remember it's dynamic. That's the whole point. But it will have to pay by doing an additional step, relocation. And this is how relocation works. It means to go and adjust the executable and all the other loaded DSOs and put the right addresses in there. And okay, there are two kinds of dependencies actually. There are dependencies which can be resolved inside the object. For example, I have an object, I'm using some sort of a symbol. It actually is defined inside my own object. So dealing with that is very simple. Basically, all I need to do is to find out where is the address where I loaded that specific object and add the address to the offset of the symbol which I have inside the object. Remember, it's all in the same object, so I shouldn't have any problem. So this is very simple to do.
You don't use a pick code to handle this?
Hmm?
You don't use pick codes to handle this kind of relocations?
Yeah, there are used. I actually didn't put any information on that in the lectures. In reality, yes, you will use pick code to handle this. And
So you will not have these relocations at all?
that's true. That's why I'm not pick code.
What's
PIC
the code?
is PIC, platform, position
Position
independent.
independent code.
Position.
In short, somebody figure out the very intelligent idea that you can put a little stab. I won't go really into the detail exactly how it's done. And then in cases like this, I don't really need to do this. But it's not very interesting because this is the simple case. And there's, I would go minus fpic, which will force the compiler to do this, which is useful, and you usually want that. Actually, I know there's some codes that actually won't run if you won't do that. I'm not really sure why. Okay, the more interesting case, though, is dependencies which are symbolic. They're from some other object completely, that we can't do this offset trick and jump into the right location. We really need to find out where it is. Okay, so a couple of things about resolving symbol dependencies, as they're called. First, there can be many references to the same symbol, and they're in different objects. The more surprising thing, that the results of lookups for the same symbol can be different for different objects. This is something which sounds logical, but if you think about it, maybe it isn't, but that's the way it is. The reason is that you've got a lookup scope for each of the objects, and the result of which symbol, which really address you want to use to resolve each symbol is dependent on your place in the lookup scope. It means that if you have several objects and all trying to resolve the same symbol, and you might have different answers when you try to resolve the symbol for object A, and different answer when you try to resolve the symbol for object B.
It means that the resolution of where is the symbol is depending on my position?
Yes, it's not really on the position of the object, it's on the lookup scope of the object. Objects are loaded and initialized according to a certain order. And the sort of, you can think about a stack or something. It's not really a stack. I'm not going to go into how the lookup scope is computed. it's very complicated, and if you want, you can look at the ELF like headers and specification. There's a lot of very big explanation about how it works. But basically, for each object, the linker will compute some sort of lookup scope, some sort of ordered set that it will go to through, actually, in order to try to find the symbol. And the order here is important. And for each object, you might get a different set. And this is actually useful. And we'll see this in
I think I lost you in the first one. When you said there are many references to the same symbol, did you mean that we're talking about different symbols?
No.
Many references, you mean that it was referred to, it was used in many places?
Yeah, you've got your executable program, you've got two libraries, and you've got the GNU-C library. All the things except the GNU-C library use printf. Okay, so printf is a symbol. It's a dynamic symbol. It comes from another object. And I will go in the program and in the two different libraries and try to resolve it. And normally I would get the same result for printf no matter what I try. But there are cases where this is not so. And I'll show an example how this is not so and how this can be useful. Okay. So this is more formally, how do we resolve this symbol? For each symbol, and we do this again and again for each symbol per object. If the same symbol is referenced a couple of times in the object, we can cache the response. But because the answer, the result of resolving it might be different for a different object, we can't cache it for a different object. So for each symbol we encounter in each object, we'll do what is written here. We'll first compute some hash value, a key for it. Then we'll go use this hash value for the first entity in the lookup scope. And the hash value is really used to compute some sort of offset into a hash table that is per object. And we go there, we end up in some hash bucket. And we simply go on basically the hash chain which is there and compare. It's actually string compare the name of the symbol there and the name of the symbol in the entry in the hash bucket. If it's the same one, if it compares true, we'll also compare version information. Again, it's a string comparison if it exists. If not, we'll go onwards to the next change in the hash. If we didn't find, we go on to the next object. And you can learn from this something very interesting, and that is that most of the checks we do of whether the symbol matches or not will fail, because obviously we'll go for each one of the objects and we'll try each one of the chains, and only one of them, the last one, will succeed, or even if the last one doesn't succeed, that's not good.
Gilad, what versions? I don't have a version on printf.
You can ask a version on symbols, and so you might say something. Okay, I have a printf, and later I might want a second version on printf, and I want to make it so that older executables will be able to use my previous version, but newer ones will find the newer version with the whatever extended facilities that it offers. And there's a way to sort of prepend version information to the symbol.
Per symbol or per object file? The version.
Good. There is
per object. I know. Dynamic library. Every dynamic library has version.
There is a facility to do version information per symbol.
Maybe
I don't know if it's actually used.
Okay.
Because usually
but
you'll just
the ELF format allows per symbol version.
Yes, it allows per symbol versions. And again, I don't know if it's actually used, because usually you just replace the library with a new version, but you can do it.
If the ELF format has a version information per symbol, while in the kernel, in the Linux kernel, the symbol protection is by appending something to the name of the symbol.
I'd say I don't know. I have no idea. I think the answer might be that the format of the kernel was actually out in the beginning, and so it might be that they invented the scheme before ELF, but I'm not sure this is the right answer.
Not exactly the same thing, because
yeah.
the symbol version in the kernel protects you from the functions
changing the
signature
parameters. That's true. It's
Okay,
doing
so
something else.
it's done in different levels. In the kernel we do it using the preprocessor, and here we're talking about.
It's not only that we do it in the preprocessor, also the version symbol in the kernel actually computes in CFC of the parameters. So it does something a little different. You can have two versions of the same symbol, but they don't change in parameters. In the kernel, those will be considered the same thing. Only if you change the parameters, you'll get a different mangling of the symbol. So they're doing it a little bit differently. Okay, so a couple of notes on optimization. We're using string comparisons to determine if a symbol is really the symbol we're looking for and the versioning. And that means that if you want to do it faster, create shorter strings, okay? And specifically, very wasteful is long strings, which actually has the same prefix in the beginning.
Which is very common.
Which is not only very common, but the C++, the standard, the mangling string actually demands it. It both creates very long strings and with a quite constant prefix. Also, ADA compiler does the same, puts ADA underscore in the beginning. And this is completely useless. It's actually hurting performance. But that's the way it's done.
By the way,
You can, but you need to do something.
If you replace all the symbols with distinct hash values of the stuff and put them at the start of the symbol,
you can do it. It's very easy to solve, but the standard just saying...
You're saying that would give a significant speed increase.
I don't know if it's significant because in reality what happens is you only pay this in the first time you're using the symbol. So you probably will shorten the load time. Sometimes very important. If you know the history of KDE, they had a big problem there. Everybody complained it's very, very slow. And the reason was just that they were loading a lot of libraries and the relocation was taking forever. So usually you don't see it. Sometimes you do. When you do see it, it's a good idea to start doing something about it. Until then, maybe it's not worth your while. But it's something to consider. If somebody comes and say...
stripping helps or...
No, it's not even loaded. The parts of the ELF executable are marked not useful in runtime, and they're never loaded, so it doesn't really supposed to matter. Okay, one more interesting thing you can do is that, as I said, most symbol lookup will fail, in the sense that we'll find some hash bucket and then we'll go through all the hash chain there, only to find in the end that this isn't really the one we were looking for. And it means that if we can get the chain smaller, we'll have less to do. And how do you get the chain smaller? You make the hash table itself bigger. Okay, so you have less collisions and you need to chain less. And actually, the GNU linker actually does a pretty decent job in doing this if you tell it to. If you give it the -O, big O flag, to the linker, not to the compiler. A lot of people, they give -O2 to the compiler, they don't give the -O to the linker.
W minus W
minus W minus WO
WL.
Oh, yeah.
WLO.
Man,
I think it's minus W, capital W, lowercase L, comma, minus O.
Just O. The minus is already there.
I can tell you the way I do it. I copy the same makefile that I copied the project before, and it's there somewhere. Okay, and in some really hairy cases, if you really have something strange, you might even, there's some flags that allow you to determine how what is the size of the hash table. And you pay by making the hash table bigger, because you make the image of the executable in memory bigger. But it will make the program load faster. If that's what you're looking for and you're willing to pay the price, this is one way to do it. Allow it to make a very big hash table. Then there are no collisions in the hash, etc., etc.
Just one more question. That is only for loading. It's have some effect in the running?
Well, actually what will happen is that the way it usually is set up, unless you ask something specific, is that the first time you use the symbol, the dynamic linker will be waking up to resolve it, and the process of waking it up will actually rewrite the jump to the dynamic linker to resolve it with the result of the resolution, which means that the next time you will use a symbol, it's just one jump. So you only pay the first time you use a symbol. And almost always it's only significant when you load. Because when you load, there's a lot of symbol resolution going on. And later on you might get some more symbol resolution when you using something you didn't use before, but you pay a very big price in the beginning. But sometimes a very big price in the beginning is also costly because you double click the program, you wait and you wait and you wait, and if it's Mozilla, you wait some more. If it's OpenOffice, you will give it more. So sometimes it makes sense to look at these things, and this is the things you can do.
Can you force all the symbol lookup to be done in the beginning?
Yes, there's actually some environment variable which I completely forgot, but it's bn_now or something very similar that says bind everything in the beginning. Now there's a great paper which I actually stole most of this lecture from by Ulrich Brepper or something like that, how to write shared libraries, and it's really good one. It goes into a lot of details on PIC and on all the things related to which I didn't go into. If you're really interested in optimization, it's a good one.
He's from KDE and they
No.
Yeah,
they had the
he works for Red Hat.
He's the maintainer of the GNU C library. That's what he is.
Okay, he's a good guy.
That's a bit more impressive than KDE.
He's the person who went.
No, I think he's the one who solved the KDE. He's got a big article on why KDE loading is so slow. And
he's the maintainer of the GNU C library, and he works for Red Hat.
I'm
Call
not
the good
working.
guys.
Okay, so we describe what's in ELF and how to use it.
Okay. Can I ask another question regarding memory management here, or like just respond
Yes,
to
yes.
the
I
question?
probably won't know to answer it.
Okay. When you load the binary file, all its pages are shared by all processes that load the same file.
Yeah.
Okay. With the exception of relocations.
So you want to ask how does
relocation interact with this read-only access to the pages in the...
the article I said before discuss exactly how it's done. There's a got table and some stuff like that. It's actually is being used to address this. It puts a little table where you jump a table and a couple of stubs. You jump to the stub, and the stub will look at the table to find where to go to, and it's a different page. Okay, so you've got everything mapped somewhere in the process space, and you've got different pages that actually contain the table and stubs. And what you need to change is basically the table and the stubs, not the pages. So it's separate, but there's a hell of a lot of details in that paper. Okay, so we discussed some of the properties and how an ELF file is loaded, etc., etc. And now let's try to have a little fun. There's one very useful feature of the LD.so dynamic linker that comes with Linux, which is called LD_preload. I'm just curious, how many people here actually know about LD preload? And okay, so at least for some of you it will be useful.
How to like to let work with LD preload.
Right, BD text.
Yes,
This is the LD preload.
That's true. That's a good example I didn't think about. Okay, so for you guys, probably going to be boring. Tough luck. Okay, but maybe I'll be able to tell you something you didn't know, and then this is how exactly this is working in conjunction with the properties of the ELF file format. If you remember, I said before that each symbol resolution happens in relation to the specific object which you're trying to resolve a symbol in, and that this is useful. And now we'll see an example of how LD preload together with this property can be used to do something useful. And something useful we're trying to do, as the people who mentioned the BD library probably know, is hijack symbols. And that is to take a program, complete running program, and change it without touching its code and recompiling it. In essence, we're trying to make it so that when the program will go to use a certain symbol, in this specific case it's a function, but remember you can hijack any symbol and just replace it. Make it called our symbol, our version of the function. And this is where the fun part begins. In that our version of the function to call the original one, which is a little more tricky than just hijacking it. There's a little bit more to do. Okay, so the specific program in question is an example, a one-liner example, which is called sleepless. And sleepless just hijacks the sleep symbol. And what it'll do is first it will print, just do a printf with sleep less, do more, and we'll then call the original sleep function from the GNU-C library, which will end up calling the kernel sys_sleep function, but that doesn't really belong here. But what it'll do, it will change the parameter you give to sleep. It will just half of the parameter. If you call sleep 5, it will call sleep 2.0. Oh, understood what we're trying to do? We're trying to create some sort of a library that will magically, one would be called the function of it, our version of sleep when the program will try to call the sleep symbol, and what we'll do is we'll print some nasty message to the standard output, and we'll sleep for half the time that the program asks for. Okay, so this is a little difficult to see. Basically, this is the source. And we need dlf_cn.h. Okay. What we have here is basically we define our own version of sleep. That's all we did. The maybe little tricky part is how to actually call the original function. Because, of course, we can define our own version of sleep that, for example, will just do the printf and that's it. It won't sleep or it will sleep in some other mean. That's easy. And we'll show later how we can load that and use it. That's not a big challenge. We'll just compile it into a standard library. We'll modify the ld_preload environment variable to contain the path, the name of this library. It will get loaded, and we'll explain how and why this will be called when the program will actually try to do sleep. The interesting part begins when we actually want to call the original function from the GNU-C library. This is hijack. And our problem is as follows. We define here a symbol called sleep. We need this symbol because we're going to replace this symbol with the original one from the GNU-C library. But inside it, we want to actually resolve all the sleep symbol. This is sort of a problem, because obviously if we just put sleep here, it'll just call itself recursively. This is not what we meant. We want another version of the sleep symbol. Luckily, there's an interface to doing that. It's called dlsim. It's Solaris originally, but somebody decided it would be a good idea to add it to Linux. And usually what you do is you use dlopen and give it some dynamic library. It will load the library, then you can do dlsim with a handle you get and the symbol, and you'll get you basically resolve that specific symbol. There's a nice hack you can do, which only works on the GNU version of this thing, and actually it's so not standard. You actually have to define __ use GNU, which I think it's subliminal message. Use GNU. And if you don't define this, you don't get the magic constant RTLD next. RTLD next, what it allows us to do is to give it as a parameter as a fake handle to dlsim. Instead of doing dlopen, we give the RTLD_next. And then what will happen is that the dynamic linker, because dlsim comes from the dynamic linker, as you see, you will have to compile it with -ldl, so it will actually find dlsim. We'll continue looking in the symbol in the lookup scope from the point where we stop. So basically, we are using this property of each object symbol being can be resolved in relation to who it is, to say when somebody else trying to resolve this symbol, give it this our version of sleep. But when I'm trying to resolve this symbol, I want to continue the resolution and find the other version of sleep that's defined somewhere.
So you're statically linking your library with the DL, or
No.
It's regular shell.
So the dynamic linker itself is a shared library?
Okay, I probably should have said it. The dynamic linker itself is a shared library, and but it's a little different as a shared library. It's called because it's automatically included in all the ELF or the dynamically linked ELF. But you do need to include some interface shared library if you want to use functions that belong to it. So you will get the dynamic linker anyway, and it is a shared library. If you do LVD on some dynamic link file, you will see it there. If you want to use the interface function, DLSyn, DLOpen, DLError, you will need to also link the shared library which implements the interface to use it, which is slightly different.
This will allow you to hijack it several times. You hijack and then hijack.
System calls?
Could you repeat the question?
I didn't try this, but I think probably it will. The one thing I can tell you is we'll see in a minute how you use it, and I don't know how to tell you how to determine the order. You probably can determine it by just trying it. The order you need of the parameters.
Who hijacks first, who hijacks second.
Right, I'm not sure, but probably you can. I didn't try it myself. So basically, the magic here, justifying the sleep symbol is easy. The more complicated part and tricky part is actually being able to resolve the original symbol, the one that we want to hide, so that it will be visible to us, but not to the rest of the world. And this is how it's done. This is not good. Use the magical _ use GNU and the RTLD _ next to tell the dynamic linker that you actually mean to grab the symbol from the rest of the lookup scope. And you need to compile this with the usual stuff. You need to link against the interface of the dynamic linker, and you want to make it a shared library. So hence the share. Okay. So this is the uses example. First, we just use time and a random test program just as sleep 5. And you'll see that actually slept 5 minutes. Then we'll run the program, but we'll set the LD preload, this is bash, if somebody's wondering. We'll set the LD preload environment variable and to contain sleepless.so, the shared library we compiled before, and we'll run it. We'll see that we'll get to the standard output sleepless do more, which means that our version of the sleep was called, and then the program will sleep for 2 minutes. The reason it's 2 minutes, it's because that's what you get when seconds, of course. It's because of round off. I divided it as an integer. So basically, what we were able to do is what we wanted to do: to hijack this symbol, this call into GNU-C, and run our own version of it, and basically call the original version with our change parameter, which is actually pretty cool. And there's some really neat stuff you can do with it. Some people already mentioned using it to do a lot of Hebrewisation of program stuff. Okay, I know that's usually, but I only have 2 slides, so I'll just share.
A question in the middle. How do I make a specific program being hijacked? I mean, how do I do this for a specific program?
Okay.
Is that next slide?
No, actually it's a previous slide.
No, I don't.
You replace your program with
you call
shell
the program,
script.
just eliminate the time here, it's just used to count. But if you just change the LD preload environment variable and call the program, the dynamic linker, which as we all remember, will be the first thing that gets run by the kernel, will make sure to load the dynamic shared library that you specified as the first one in the lookup scope. It will be the first one it will load regardless if the executable needs it or not. And it will use it as first thing to try to resolve all symbols. Hence, when something in the executor will try to resolve sleep, it will first try to resolve sleep here.
Okay.
That's why it will get our version.
So it didn't change. So this was. I mean, if I went back to time dots /test, on the next line I would get 5 seconds again.
Right.
I didn't set the shells, my current shells.
Ah, no. This affects only this run.
This is my bad knowledge about shells. I'm sorry.
Okay, it affects only this one. That's the way Bash works. But
Okay.
So there is no hierarchy here. I mean, there are objects, shared objects that get loaded first.
Well, this is. I know you can pass actually several lines here. I don't know who gets first. Yeah, you can put several libraries here, and they'll all be preloaded. I'm not sure about the order. I'm not sure there is a guarantee about order. It's very possible there is. But if you need several libraries, I mean, you're really doing something funny.
Another real backwards question. At what stage, I suppose the linker should do it if anybody does it at all, the point where you check that parameters are really the parameters the function expects to get?
The linker does some sanity check on it.
At what point?
I know that I read in the Draper paper where does it do it, but I don't exactly remember. It's during symbol resolution. If it actually if I remember correctly, it's when it finds a match in the symbol name and version information, if exists. It will also do some sanity checks according to this, but no guarantees.
I'm not sure it does parameter check.
It has very limited.
It's not.
I think it only does name check.
It doesn't. I don't know if it does parameter checks. I know it does some sanity checks. I'm not sure exactly what's the nature. It's not types, obviously, but it might be sizes, which I know it does. So it's not types, but it's sizes. If it's a different size, it will know because it needs to know what class. That's my best guess. Okay. We move on, and okay, there are a lot of useful things you can do with LD preload, and there's supposed to be preload, whatever. And for example, there's the run socks, actually script and library that is used to run any socket using program and to sockify it, to make it use socks 5 proxy on the fly while change the program. That can be useful. Sometimes things are not so simple. For example, if you try to hijack the open symbol from the GNOME-C library because, I don't know, you want to make some sanity checks, you want to make a union mount, all sort of things, you'll discover that yes, you can hijack the symbol, but a lot of calls in the GNOME-C library actually call that symbol internally, or rather, they don't call that symbol, they call _open, and the problem is _open isn't exported, so you can't hijack that, it's not exported, you can call it. And if you really want, you can just change the source to export it yourself, and you want to do something like that. But you need to remember that if you ever try to do anything weird with the OpenSys call or other system calls related to files. And of course, it can also be a big security risk, because if you can affect somehow root or somebody else's environment variable LD preload, it basically means you can get them to run any code you want at any stage of a program. This is the reason why the dynamic linker will not respect LD_preload with setuid binaries. And so if you experimenting with this and you run some setuid binary and it's not respecting LD preload, it's trying to protect you from yourself, and probably does a good job. Okay, this is the last slide, so you can relax. Linux kernel loadable models are also ELF formatted dynamic shared objects. They're very similar to shared libraries. They're of course linked against the running kernel. The thing that does the linking is the insmod utility, as I said before, not in the newer kernel versions. And you can do all sort of tricks like LD preload, of course not with the LD preload environment variable. I'm leaving the exercise of find out exactly how to use. And all I have to say is you are the weakest link. Goodbye. So if anybody has questions?
Now about embedded Linux. Brian can back.
Question. If the dynamic linker is a userland mechanism, how does it make sure that all instances of a shared library occupy the same memory space?
It just maps them. I'm not sure I understand the question. I'm not fully understanding the question, but basically it will map them.
If several processes load, say the standard C level. Yes.
Okay. Mmap accept the flag mmap shared. So it'll basically what happens in all the programs, mapping shared memory basically. That's how it does.
You said that the kernel has its own versioning system and gives IC functions like mmap and old mmap.
Yeah, that's different. That's different.
Yes, I understood it's different.
The versioning system it uses for its own function. Mmap, old mmap is actually for use of exporting the things outside for system calls, etc. It's a different thing. It's for the binary API.
Compatibility.
Right, and not for something you would use inside a kernel, which is different.
You have all binaries which expect the mmap system call to have this many parameters and to be system call number 11, okay? And you want to change the parameters of mmap and you want to give it a new system call so that all binaries will continue to work.
The point is that the versioning system relates to calls inside the kernel. And what this is relates to calls from outside into the kernel.
So the kernel has its own versioning system inside the kernel, and everybody else has another versioning system, but when the kernel comes to interact with the user space, it doesn't have any versioning system.
Because it's half true because there's a layer of compatibility which actually shields everything. And that's usually a GNU C library or some related library. So you don't really need a versioning system because what happens is you change just the GNU C library and everybody becomes aware of the changes. You don't need a versioning system if you only have one contact place. And they're just kept it simple. If you run static libraries, then that's why the backwards compatibility is for. But it's limited enough that they didn't bother to do it.
How is all this all related to kernel loading?
Okay, the Linux kernel modules that you load is, you can think of it exactly as a shared library, which you load. It's pretty much the same mechanism. It's straight elf. There are some of the sections are a little bit different, but not very, very different. And it will do the same thing. It will mmap this into a region of space. It will relocate all the symbols. The only difference is that the symbol it will use to relocate are kernel symbols and not of the program or the others DSO. So it's pretty much doing the very same thing that the dynamic linker is doing. And you can work the same tricks, although it's a little different.
Another thing that there is in the Linux in the kernel modules that you don't have in a dynamic link library is that you have a usage count, which the module can increase when it's opened and decrease when it's closed.
It's true, but if I'm not mistaken, even this is implemented as one of the non-standard ELF sections, because ELF allows you to define like additional sections, and you can put extra stuff in there. So this is one of the stuff which, as far as I know, they put in there. And practically, you can implement the same thing for a shared library if you want. It's just not part of the standard API.
It also makes no sense.
Actually,
nobody is going to unload the library in the middle.
Yeah, actually, the dynamic linker does keep a reference count. Yes, because it needs to know when to unload the library. It's just not done. The model itself, usually, as far as I know, the shared library doesn't have access to that information, but the dynamic linker does keep that information. It's just the same thing exists, just exists in a different place.
Another issue about relocation. How is it actually done? Is it actually adding, going through the code and adding new places?
Well, no, I didn't. It's actually related to what we talked about with the pick. And there's two tables. One is called GOT, and the other one
ELT.
Yeah, something like that. And basically, the way it's done is you have a table, and it's filled with the real values. And for a symbol which isn't a function, it basically just use the address of the offset into the table as a relative, not relative.
It's a vector.
Yes. And if it's a function, you also, in addition to this, have a couple of stubs. But basically, all they do is, if you haven't used that specific stub before, we'll jump to the dynamic linker to find out which the address. and that process will actually put the answer so that it will replace the stub to go look in the table next time. So what?
And regular variables?
Regular variable are just entries in. You reference them indirectly, okay? And the address you use for the indirect reference is in that table. So basically, you have just a table with the addresses, and by using the offset, you can, just go to the right offset, which you can compute somehow. Change the address which is there to refer to whatever summary you need.
Another thing that is maybe worth mentioning is that if you're writing a library, make sure that everything that should not be exported won't be exported, because the default is to export things. So mark functions as static in file scope and mark variables as static in file scope if they're not supposed to be exported. Okay? And the kernel, for example, handles this explicitly. You have to mark symbols as exported, otherwise they aren't.
So you still have the problem of this table, right? Having a different address in different processes.
Yeah, but it's per process. There's the pages basically of the shared library, and there's the table and the stubs, and they're not on the same page. So
yes, but
this is shared. This is.
But the question is, this table, okay, is it located always in the same virtual address in each process, which might be in the different virtual addresses in different processes?
Oh, now I understand the question. I don't know. I don't really know.
Because if it has a different address, then you cannot.
Because it's per process and dynamic, then I would guess that it's always in the same place, but it only gets created